Okay, so the first step in our RNA-seq data analysis workflow is the quality control of raw reads. And by raw reads, I mean the FASTQ files that we got from the sequencing device or the sequencing provider. And we do the quality control to see what kind of problems may underlie in your data. We cannot always correct the errors or problems, but it's good to know that they are there even though you cannot do much about them. In many cases, however, you are able to do some corrections like trimming and filtering, which we will go through briefly after a while. Potential problems that can be found in your data are, for example, low confidence spaces marked with N. So in those cases, the sequencing device didn't know whether it should be A, T, C, or G base in the location, so it just puts N instead. There can be sequence-specific bias, GC bias, adapters left in your data. Those are, by default, those are usually removed by the sequencing provider, but there might be some left still. There might be also some sequence contamination in your data. So for example, if you have, let's say, rat data or rat sample, there could be some human contamination that happened during the processing, for example. So these are the things that we are looking for. There are many software packages available for quality control. Here I mention few. In Chipster we have these options, and today we are using FastQC, which is probably the most used one. It's very nice graphical. It gives you a nice graphical result file, and it's the one people most often refer to. A couple words about the FASTQ file format. So I already mentioned that that's the raw format that you get from Illumina sequencing devices. In FASTQ files, you will have 4 lines per each read. So here in purple you can see those 4 lines represented. So first there's this @ sign and then the read name. So that's the first line or row of the data. Then on the second line comes the actual sequence, so G, A, T, T, and so on. So these are the bases in your read, in this particular read. So here you have as many bases as you had cycles in your sequencing run. So if it was 75 cycles, it means that you have 75 bases long read here. On third line, you just have plus sign there, and then the read name or some other information regarding the read. Again, it might be empty as well, but there's always the plus sign. And then the fourth line looks a bit curious. So these are ASCII characters which represent the quality of each base here. So there are as many characters here as there are bases here. I will shortly tell you more about these quality values in a moment. If you want to know more about the FASTQ format, the Wikipedia page is actually quite good, so you can go and check that. And then there's a little reminder that in Chipster you don't have to unzip your FASTQ files. So it's totally okay to deal with those .gz files that you get probably from your sequencing provider. So of course then you cannot look at the raw data as text like this, but you don't really have to, so it might be very advisable to leave them zipped. It will save you time and space as well. So then I promised to talk a little bit more about those base qualities, so those weird looking characters in the fourth line of the FASTQ file. So the qualities are given as these so-called Fred quality scores. Here you can see the formula. So if we have a probability that the base is wrong, then the probability for that is 0.01. If you take the Fred score out of that, we get 20. So 20 means that the probability that the base is wrong is 0.01. Now, why do we want to do this conversion? Well, because often the probability is very low, so the quality is very good. So in that case, you would have many zeros here, and it's sort of tricky to look at. And also this log scale makes the plots much nicer. So that's why we use this Phred quality score. So here you can see an example of that. So for this first base here, T, the quality would be 40 and so on. Now, to make it a bit more complicated, maybe, they wanted to save some space still, because there are many reads in your data, and if you would write for each base these 3 characters there, so 4, 0, and then the gap, it would take a little more space than instead using these ASCII characters. So that's why they decided at some point to transfer these values into these well, characters, letters basically. So they decided that they just start. So here we have the ASCII characters in black. So they just decided that they start from the exclamation mark and make it so that the Phred quality score of 0 is represented by the exclamation mark. 1 is this this mark, and so on. And the exclamation mark is actually the 33rd character. So there's characters before that also, but they just decided to start from here. Now, during the early days of next generation sequencing, they had a little bit of difficulties to decide which which characters actually to use for the quality control. So as you can see, this purple one starting from 33, that was the first guess, but then they changed it along the way, so they started from different characters in between. And now they are back in this original 33 option. So why am I telling this long story? Well, because you sort of have to know how the quality is encoded. Because if you would, well, you can imagine if you use the wrong encoding, it will cause problems when estimating the actual quality later on. So luckily, the tools like the FastQC that we are using today will tell you which encoding is used. So these are the names of the encoding. So usually you see this Phred 33 or sometimes Phred 64. So what you have to do when you get your raw data, you do the quality control, and then you check which quality encoding is used, and then you just have to remember it and give it to the tools as inputs later on. Luckily, now we are mostly dealing with this Phred 33 data, so this is it's very likely that this is the encoding your data is using. But if it's an older data set, or you download it from some storage, it could be something else as well. So keep this in mind. And you don't have to really watch these weird-looking ASCII characters, or actually the whole FASTQ file as text, if you don't want to. It's not very human-readable in that sense. Instead, we use these tools like the FastQC to give you more informative ways to check your data. So here's one of those example of one of those. So this is the per position based quality plot from FastQC. So this is the plot that you usually look at first when you get your data. And how does this work? Where here in x-axis you have the position in read, so it's going from 1 to 40. So this is a 40 bases long read. 40 bases. The reads in this data are 40 bases long. And in y-axis you have the Phred quality score, so it goes from 0 to 38. And then they have this nice color coding here. So green area means that it's very good, the quality in that that location is very good. Yellow, it's okay, and everything in red area is considered bad. But this is just how the people who develop FastQC see it. It's not necessarily the universal truth about the issue. So in this case, our data looks very good. It's all in the green area. The blue line here, that's the mean quality in that location. So, for example, let's see in the very first base in all reads, the mean quality is 37, and so on. The red bar, which you can see, well, maybe there, that's the median value, and these are the quartiles, and these are the whiskers. I think they are for 10 and 90%. Sorry about that. So what I was saying is that the things are not always that rosy. This is the exactly same plot for different data. In this case we have 75 base pair long reads, and as you can see the quality is sinking now towards the end, and it's not that super good in the beginning either. So something's not really that optimal here. Maybe the library preparation wasn't perfect, maybe the data or the sample was not that good in the beginning. So for this data I think we should do some trimming and filtering to get it in better shape. So these are just to give some examples of how it can look like and what you're looking for when you check your data. Another little reminder, so FastQC gives you several plots, and this is the traffic light plot seen here is just one example, and this is another one, preposition sequence content, and this is just to give an example and notify one little thing regarding this this plot when used in RNA-seq data. So again, this plot shows you the read. So this is again for the basis long read, and here you have just percentage, and the 4 lines here, they represent the different bases. So red is T, blue is C, and so on. So what you would expect is that you have roughly equal amount of different bases in every location of the read. So roughly 25% of each base all along the read. So this is an example of what you could expect. But this is what you see usually when you have RNA-seq data. So there's something funny in the beginning. For example, you can see that in the very first location, the base is with 55% certainty it's C, because that's black over there, and the second one is green, so that's like 50% of them are T, and so on. And this is because of how the library preparation is done. So they use random hexamers or transposases in the process, and they are not that random really. So they tend to prefer certain sequences in the beginning of the read. So this is something that is really typical for RNA-seq data. It can't be really corrected, but luckily it doesn't usually affect the analysis. So even though the FastQC will give you like an error or exclamation mark that hey, there's something that you should take care of here, it's actually nothing that you can really help. It's the actual sequence, so you don't even want to remove it or anything, but it's just again, it's good to know that this happens. So don't worry about this, it will happen if you have RNA-seq data that is made with random hexamers or transposases. So after the quality control, we might need to do some pre-processing, trimming and filtering, depending on how our data looked like in the quality control phase. So what do I mean when I talk about filtering and trimming? Well, filtering means that you're removing the whole read. So if it's, let's say, on average it's below certain quality, you just remove the whole thing. Whereas when trimming, you remove only the bad quality bases, so the bad part of the read. So let's say that for example, in the poor looking traffic light plot, the yellow bars were sinking towards the end, but the beginning was maybe of better quality. So then you would just trim the end of the read and leave the beginning. Of course, if it's bad all the way to the end, to the beginning, then trimming also removes the entire read one by one. Well, naturally, trimming makes reads shorter, which might not be that optimal for some applications. And for example, if you try to align read that is, let's say, 5 bases long, you can easily imagine that it will align to very, very many locations, and that will then only take your time, and it won't produce any meaningful results. So that's why when you do trimming, you usually want to make sure that your reads are not shorter than particular length. Then there's a reminder, if you're dealing with paired end data, like most people these days are, remember that your reads have to be in matching order in the two files. So when dealing with paired end data, you will actually get one file for the first read, and then a second FASTQ file for the second read. And always in those files, the reads are in the in same order. So if you decide to filter one read off from one of the files, you have to also remove it from the other one. So luckily, many of the trimming and filtering tools will take care of this, but you just have to remember to give both files to these tools and select a tool that can handle these things. Okay, so then in the quality control phase, I was talking about different level qualities. So as you maybe remember, in the traffic light plot of FastQC, we saw that some value was chosen as the limit for green area and so on, so the good area. And also I was talking about filtering and trimming reads based on some quality threshold, but what is now a good threshold? There's really no consensus yet. There's a lot of talk about the issue in for example, these papers. It's always anyhow a trade-off between having good quality reads and having enough sequence. So if you decide to, that you want just the very good quality data, you might end up throwing away a lot of maybe not that optimal quality, but still usable data. And the other way around, if you save all the data, the rubbish might take your time and cause you false results later on. So it's sort of a trade-off always. And what we suggest and what we do in the exercises is that we do very gentle filtering and trimming in the beginning and see how that affects the quality. So we do FastQC, then we do some trimming and filtering, and then we do FastQC again to see if it worked. And if the gentle, and by gentle filtering I mean using very, not that like high thresholds for the quality. So if that works with the gentle trimming, then we are happy. And if it didn't work, then we just do a little bit more or change the parameters so that the threshold is a bit higher. That's my suggestion for that situation. Again, there are many packages for pre-processing as well. We have many of those in Chipster as well, and today we are using Trimmomatic, which can handle parent data, and it can do many things in one go, which is always nice. So here are some options for Trimmomatic that you can use in Chipster. So you can remove adapters, and then of course the minimum quality is a parameter. So you can do trimming like per base, one base at a time, or using this sliding window from either end of the read. So sliding window means that you're looking at the quality in a window of bases that is sized well, I guess you can determine the size there as well, but for example, let's say that it's 8 bases or something. You can do also this per base adaptive quality trimming, which will optimize the trimming so that you have nice length reads that don't have that much error still. So it's optimizing between the length and errors. Or you can just use the minimum mean read quality. You can just choose to trim number of bases from left or right. So let's say that your first base or very last base is somehow looking very bad, so then you can just trim that one away. And then you can set, like I mentioned, that the trimming always makes the reads shorter, and you don't want to have these very, very short reads there, so you can remove those after trimming by setting this minimum read length. And Trimmomatic copes with parent data, which is a good thing. So you just have to remember to give both files as input.
Okay, so I guess we are now ready to go through the questions from 1 to 5. So I hope you can see it's a little bit tiny, but I made it a bit bigger from here. So this is the workflow we are checking now. So question number 1 was about the FastQC report, and it was that how many reads does the FastQ file contain? So we need to open the FastQC report in external web browser. And here we are. So how many reads do we have? We have the number here, so it's the total sequences. And many of you got it right, so good job. Then the second question was that how long are the reads? So in the very first plot, again, you can see here the sequence length is 75. You can also see it from the plots because they go from 1 to 75. So we have 75 base pair long reads there. Then the third question was yes or no type of question of how is the base quality along all the reads, and this is the plot you want to be looking at this point. And well, the answer is that the quality is not that nice, so it's sinking towards the end of the read, and then there's this weird hiccup here in the middle. So then if you check also some of the other plots, so you can see here list of all the different reports that we have in this FastQC tool. So you can see that some of them are red. It means that something is maybe not optimal in there. The green ones, they are okay, and yellow means that there might be something funny there. So if we look at the red ones, so first is this one, which we just checked, and yeah, it's sinking towards the end, and then there's the hiccup, and the other one is this per tile sequence quality. So that's sort of showing the locations on the flow cell. So there as well, you can see that there's something funny happening in the cycle number 40, so in the base number 40, at the same locations that we see here. Okay, then after we checked the quality, we did some trimming with Trimmomatic, and there was a question regarding that as well. So we asked you to check the log file after the trimming. So it's this one, and you can view it as text. And there's just a little bit of information on the Trimmomatic tool. So there's the command or the parameters that you use to run the tool, and then the number of input reads, and how many of them survived the trimming and filtering, and how many were dropped. So I think we asked how many reads were dropped. So 12,621 were dropped. So that's the answer to question number 4. Then after the Trimmomatic, we did the FastQC quality control again. So the same thing we did for the raw reads, we now did for the filter and trimmed reads. And again, we can view that in the external browser, and it's giving the same plots for you. And I think we just asked, is the quality now improved? And if you look at this plot, well, yes, it's improved. It's not sinking to the red area that much anymore, but there's still this hiccup happening here because we started the trimming from this end, and because there are some good quality bases here in between, we never reached to this base. So that's left there. Luckily, it's not that big of a problem later on, so we don't have to really. We just have to remember that it's there.